and welcome to the first and only episode of Film Astronomy Explained. Today, we'll be talking about Christopher Nolan's first and only introspective movie, Interstellar. Interstellar follows Cooper, a former NASA scientist and engineer who was sent on a mission to find another inhabitable planet for Earth as it's slowly becoming uninhabitable due to dust storms and crop lights. The sci-fi film, released in 2014, surprisingly used a lot of real science to construct the intricacies of the storyline, with American theoretical physicist Kip Thorne by Nolan's side the entire writing process. Today, though, I will be specifically talking about black holes. The three topics I'll be fact-checking from Interstellar are what black holes look like, how time dilation works, near black holes, and finally, what happens inside of black holes. Let's get into it.
Part 1. The Heart of Darkness, Gargantua.
The supermassive black hole in Interstellar, also known as Gargantua, was visually crafted through hundreds of hours of CGI simulations and astronomical equations provided by Dr. Thorne. GSU grad student Mara Shea visited our class to help break it all down. She explained that to collect data on black holes, a telescope the size of Earth is needed. This is where the Event Horizon Telescope, also known as EHT, comes into play. The EHT is an international collaboration of astronomers working to capture images of black holes. At this time, the EHT have collected images for the closest black hole to Earth in the galaxy Messier 87, and it looks like this. In this image, we can see the accretion disk of the black hole. Although it is a little blurry, Shea explained that to improve the quality of imaging, the EHT would need to be larger in size, meaning that the baselines between the telescopes will have to be bigger. For this, telescopes in space would be best. So, although the black hole in Interstellar doesn't look exactly like the one we've gathered from information, it doesn't mean that it won't be like that in the future with better imaging.
Part 2. No time for monkey business.
Interstellar deals with Einstein's theory of relativity a lot throughout the part, but a specific scene comes to mind when discussing time dilation. Two of the planets that Cooper's team is observing are extremely close to Gargantua, one of them sitting on the Event Horizon, otherwise known as the point of no return. See, despite media representation of black holes sucking everything in around it, black holes don't actually suck anything at all. While it is true that nothing can escape a black hole, GSU astronomy professor and astrophysicist Dr. Ginsburg explained in class that if the sun turned into a black hole today, the Earth would continue its orbit. This is because it is only at the event horizon, past the accretion disk and past the innermost stable orbit, where objects cannot escape. So since Dr. Miller's planet is sitting extremely close to the black hole, Einstein's theory of relativity tells us that time works differently. In the film, the crew explains that due to the black hole's massive gravitational pull, time will be much slower on the planet than it is on Earth, causing a major discrepancy. Romilly, one of the crew members, explains that for every hour on Miller's planet, 7 years will have passed on Earth. So, is this how it works? Well, Einstein's theory of relativity explains that in the presence of mass, space-time can bend to take the shortest path. This means that objects closer to a massive body, say a black hole, will experience time much slower than objects that are further away. This is why time near Gargantua would be much slower than the time on Earth. The difference in elapsed time between the two objects, in this case the black hole and Earth, is called time dilation. The 7-year difference that Romilly hypothesized is the time dilation between Earth and Miller's planet. So, although we can't be exactly sure that Romilly's math was correct, the time discrepancy is real. So, what exactly happens in a black hole? Can a lonely and desperate astronomer save the world by communicating insanely complicated quantum data that proves gravity can cross all of the dimensions, including time, to his 10-year-old daughter? Well, quick answer, probably not. Long answer, we don't really know. Currently, there is no way to identify what exactly happens in black holes. According to our class OpenStack's astronomy textbook, since general relativity tells us that gravity is the curvature of space-time, as the gravity of a black hole increases, the curvature also increases. Light tries to escape, but since space-time has collapsed in on itself, all of the paths that once led out have now become curved paths that lead back in. This means that anything that tries to escape cannot, seemingly destroying all information that enters. This is called the information paradox. There are two different theories to try to explain this. First, the disappearance theory, which states that once the whole evaporates, all of the information stored within it evaporates as well. This is based on the theory that empty space is full of particle-antiparticle pairs that pop up in existence due to quantum effects and correlate with each other. The pairs annihilate instantly and carry negative energy inward, causing the black hole to lose mass until it eventually evaporates. The second theory, firewall, predicts that information stored inside the black hole is carried out by quantum correlation among all the particles which radiate from the black hole. This requires that radiated particles break correlations with their partners, and then the energy released from this separation creates a firewall around the black hole, in which the correlations between the emitted particles contain all of the information about anything that fell into the black hole. Unfortunately, there is no information stored in the singularity of the black hole, which will hold the quantum data to solve the problem of gravity. Nonetheless, Interstellar did a great job of combining astronomical data and theories with science fiction to create a beautiful film that actually helped theoretical physicist Kip Thorne develop 2 scientific papers about the behavior of black holes. Well, that's it for today, folks. Thanks for tuning in to the one and only episode of Film Astronomy Explained. And remember, if your child says they have a ghost, make sure it doesn't hold the quantum data to solve the problem of gravity and potentially save humanity.